Those two small bumps on your keyboard have prevented more workplace disasters than any ergonomic chair ever sold. The F key and the J key each carry a small raised ridge, sometimes a nub, sometimes a bar. And if you have never consciously noticed them, that is exactly the point. They are designed to be felt, not seen. Stay with me. You will learn why those bumps exist, why only two keys have them, how they connect to a century-old typing discipline, and why removing them would make even fast typists dramatically slower. Most people assume keyboards are just grids of letters arranged arbitrarily. They are not. The QWERTY layout was locked in by the 1870s on manual typewriters, and the entire discipline of touch typing, hands on keys, eyes on the page, was formalized in the decades that followed. By the time IBM was shipping the Model M keyboard in 1984, a global workforce had been trained to type without looking down. The bumps are infrastructure for that skill. They are the tactile anchor that lets your fingers find home row. A, S, D, F on the left, J, K, L, semicolon on the right, without your eyes doing any of the work. 2 bumps, 8 home row keys. That asymmetry is the whole trick. Here is the mechanical logic. Touch typing is built around one idea. Your left index finger rests on F, your right index finger rests on J, and every other finger falls into place from there. The thumbs hover over the spacebar. From that home position, every key on the board is within a 1 or 2 key reach. You never have to look because your hands always know where they started. The bumps are the reset signal. After you have stretched to hit a P or a Z or a backspace, your fingers drift back, find those ridges, and the whole coordinate system reestablishes itself in under a second. It is proprioception turned into hardware. Your nervous system does not need your eyes because it has a physical reference point baked into the object itself. Without those bumps, that reset costs a glance downward, and a glance downward at 80 words per minute costs you about half a second every time. Across an 8-hour workday, that adds up to lost minutes. Across a career, it adds up to lost hours. Now consider what happens in industries where this gets taken seriously. Court stenographers, who routinely hit 225 words per minute on a stenotype machine, work entirely by feel. The machine's key layout is built around chords, pressing multiple keys simultaneously, and every single key is identifiable by position alone. No bumps needed there because the whole geometry is the reference. But on a standard QWERTY board, the geometry is too symmetrical. The rows are staggered slightly, but not enough to anchor your hands reliably. F and J are the only keys that sit under your 2 index fingers in a neutral position, which makes them the only candidates for the bump treatment. You could not put bumps on all 10 home keys because then the bumps stop being signals and become noise. The contrast is the message. 2 keys, 2 bumps. The deeper reason this design works is that it exploits a real limit of human attention. Cognitive load research from the 1950s and 1960s, building on the work of psychologist George Miller, established that the working mind handles roughly 7 chunks of information simultaneously before performance degrades. When you type while reading a source document, your eyes are occupied. Your working memory is occupied parsing words and meaning. If you also have to route visual attention to your hands, you are asking the brain to juggle one too many streams. The bumps offload that task entirely to the fingertips. Tactile feedback, texture, resistance, position, runs through a different neural pathway than vision. It does not compete for the same cognitive bandwidth. A bump on a key is not a design flourish. It is a piece of neurological engineering built into a $12 piece of plastic. The failure case is instructive. In the early 2000s, several laptop manufacturers started producing ultra-flat keyboards, particularly some chiclet-style boards, where the F and J bumps were so shallow they were nearly imperceptible. User complaints spiked in workplace ergonomics surveys. Fast typists reported increased error rates. One internal IBM ThinkPad usability review from around 2004 found that home row repositioning time increased measurably on keyboards, where the tactile nubs fell below a certain height threshold. The fix was simple: make the bump taller. The lesson was relearned. You can flatten a key, you can shrink a key, but you cannot remove that bump without paying a real performance tax on every user who types without watching their hands. This same logic shows up in other objects you handle daily. The number 5 on a phone keypad has a raised dot. ATM pin pads follow the same convention. Many industrial control panels use textured or shaped keys, so operators can navigate them in low-light environments or without breaking eye contact with a process they are monitoring. Braille is the extreme version of this principle, an entire written language encoded entirely in raised dots, because the fingertip is a remarkably precise sensor. The keyboard bump is a quiet cousin of all of these. Same idea, smaller intervention. Those two ridges weigh almost nothing. They cost almost nothing to mold. They add no complexity to the manufacturing line, but they carry the accumulated knowledge of over 100 years of typing practice, ergonomics research, and human factors engineering. The next time your fingers find home row in the dark, that is not habit alone. That is good design doing its job silently, exactly the way good design should. If this is your kind of thing, the why behind the everyday, Object Theory drops new ones Monday, Wednesday, and Friday.